Good afternoon. I'm Dr. Dimitri Yatsenko, and I would like to introduce you to the DataJoint element for visual stimuli. This module, this software module, is written in MATLAB and it uses Psych Toolbox. It's a complete application that presents the stimuli in a way that can be synchronized to other modalities of neurophysiology recordings and can be in the results of presentations, and the stimulus parameters are all recorded in a database schema. So you can find the element at GitHub, DataJoint element visual stimulus. And now I will demonstrate how it's, you can follow the instructions to set it up. You need to install Psych Toolbox, and I assume that DataJoint is already configured for MATLAB. So you can follow the instructions in the DataJoint for MATLAB tutorial to set it up. So with this, let me start MATLAB. And while we're waiting, so I already cloned the element to a local directory. So let me first set the paths. So I wrote a script, the startup script. Let me show it to you to set up the paths, and you will need to do something similar. So first you will need to set the paths for DataJoint for MATLAB. You will need to set up, so you will follow the instructions to set up DataJoint for MATLAB. Then you will need to set the path to DataJoint visual stimulus, the visual stimulus element. For DataJoint configuration, sometimes by default, the TLS is not set. You need to set it to false or true, depending on how your server is set up. And to activate the schema for the visual, for the stimulus, if you're using this for the first time, if you're using the schema for the first time, you need to create the schema on the database and associate it with this folder. So this is done with this command, dj.create_schema. Stimulus is just the name of the package. It's the same as this plus folder. Then the path, it's the same path as above to the element visual stimulus. And then this is the name of the database. And it can be, let's call it this stim, for example. So that's just the name of the database that will be created on the server. So with this, you can now execute this command. So run dev startup. So this schema already existed on in my case. And now okay. All right, so you will need to put the same schema name in this folder and in this get schema object, so that the name of this schema name needs to be the same as the one you created. So this is just how DataJoint connects the local package name with its schema. All right. So next, so right now it's empty. DataJoint does not create tables until they're used for the first time. So I just happen to know that, so if we show the stimulus, if we show the entity relationship diagram, the diagram of the schema, there's nothing in there yet. So if I do ARD stimulus, there's nothing in there. It's empty, but I know just by listing the available names. I know what tables exist in the schema. So for example, one is for session. So this is our stimulus session. So now I just created the stimulus session table. And the first time you invoked it, it creates it in the database. So for us to show stimuli, we need to enter a session, a stimulus session. So let's enter a stimulus session. And you can look at, by reverse engineering the stimulus session, you can see that it has a timestamp that's entered automatically. Now it's called describe stimulus session. I forgot how to clear the screen. Okay. Describe session. All right, so it has a session. It has two fields. The field session with of the type integer, and the session date time is entered automatically. So let's insert. So we just entered session number 1. Stimulus session. And another session, and just a few more sessions. So now here's my stimulus session table. Now, now let's look at available stimuli. And there are just 3 stimuli presented here. So one is called grading, or edit. And so to present the grading stimulus, it's called grade. So this stimulus has a few parameters, and they are recorded as attributes in the parameter table for stimulus grade. So one is the monitor to distance ratio. This is the distance to the screen measured in screen diagonals. This is so that we can accurately set the spatial frequencies pre-blink in seconds. This is the blink preceding the trial. Direction. This is the direction of motion. Spatial frequency in cycles per degree. So typical frequencies would be, say, 4 cycles per degree. Or 0.004 cycles per degree for mice. Temporal frequency would be, so for example, 2, 3, 4 hertz is typical. Aperture radius. This is the radius of either circular or rectangular aperture. So you may want to show the grading along the whole screen, or you may put it in an aperture, in a circular aperture in some part of the screen. So then you have the X and Y coordinates, and this is expressed in units of the half diagonal relative to the center. So we'll show what that looks like. The initial phase of the grading and the duration of the grading. So this is, and so for each class, so you define, this becomes a table in the database, but you also need to define a method called show trial. And this uses, takes a structure condition, which contains the specific parameters for a given trial. So it knows this function needs to display itself on the screen. And it uses cycle-box functionality. One important part is that at each frame, we need to call the flip, self.flip, and this will we'll show what that does. This is for synchronization. So flip actually displays on the screen, but it also draws a little square and for synchronization purposes in the corner of the screen, which you can pick up with a photodiode. So this is what we have now. Let's just demonstrate. So this is the first thing you need to do, basically to define a single condition. And then there is one more function you need to write. And it's in the configuration subfolder. So stimulus conf, great. So I also called it great, but lowercase in the configuration subfolder. So what this does, it gives us the controls, or gives us the sequence of commands that is needed to set up the stimulus. So first we get this object from the core functionality of this application that gives us the control. Clear all clears the queue for all the trials. Then we define the parameters of the stimulus. And for example, and you can define several different values. For example, for directions, we go with 15-degree increment from 0 to 360. So all the directions with 15-degree increments. Spatial frequency, temporal frequency, the aperture radius. Again, this is expressed in the units of the half diagonal of the screen, and then the aperture coordinates. And the initial phase would be 0, for example, in the cases. So we assert that one of these is a scalar, but then this framework comes with this function called Factorize, which takes any vector, like here, for example, we have some vectors, 2 values here, 2 values here, and a bunch of values here. And then it will factorize. It will produce all the permutations, all the possible combinations of these vectorized values. So after we are done executing, and I can put a breakpoint here, you will see that there are many parameters. Params now becomes a vector of many different stimulus conditions. So, and then we make conditions, which make conditions will further expand and add this, pre-compute any values that need to be computed from the parameters that you specify. This is a very small, simple stimulus, so there's not much that needs to be added. Then we need to use this control object and to push trials onto the queue. So one thing that it does here with all these permutations, in 3 times, it will push, well, first it will plot the total duration. So it will take the duration found in the stimulus, then multiply by the number of blocks. It will also add the pre-blank period. And then it will add it 3 times to the queue. And each time it applies a random permutation. So these conditions will be the same. Conditions will be repeated multiple times. So let's configure the stimulus for display. So to do this, we run the function stimulus configure, and the configuration script. So just to demonstrate here what we have params here. So right now it's a single value, and then we step over this function. And I forgot to step over. So right now it already pre-configured all of them. So it exited. So I didn't know how to step over. All right, a little rusty on MATLAB. All right, so params, it computed, it produced this many different conditions. So now I just need to open the screen, open the display. And right now it's configured to be open only in one portion of the screen, but typically you set up for the whole screen and a separate screen. Okay, it's setting up the parallel pool so that it can log to the database in a separate thread. Stimulus run. And so now you need to give it the primary key of the session that you need, for which you're logging these trials as a struct. So we're doing this for the first session. We're starting, and it's running. So it gives. So this is displaying it. It produces these sounds. You can turn the sound down. But this is so that while you're doing the experiment, you know that the stimuli being presented, just an auditory cue. So this is how we configure it. We configured a randomized sequence. So at any point you can do control C, and if you do so, it will pause the stimulus, and then you can continue stimulus run again, and it will just pick up where it left off, or with the next trial. It will interrupt the ongoing trial and will not replay that one that you canceled, but it will pick up the new one. So it will just continue. All right. So now let's look at our diagram. So now you can close the screen, stimulus close. And now we can look at the diagram, what this looks like, and to show how you can query the data. So ERG stimulus. So you have these 4 tables now. This is the stimulus session with which you have associated trials. Stimulus condition, the condition table contains the general codes for each stimulus. So the condition hash, this is the hash of all the parameters, including the version, stimulus type, and this time in this case is grading, and the version of the stimulus. So, but the details for each stimulus type are stored in the specific condition table. So in this case, this is the grading. And so you have the condition hash, the same as the condition. This is the primary key. The monitor distance ratio, all the parameters for each condition. Now for each, these are just the conditions. These are not necessarily trials that have been shown, but the trials that have been shown are in the trial table. Stimulus condition, stimulus trial. So stimulus trial is associated with the session, stimulus session, and it has a trial ID number. It points to the condition that was associated with the trial. So there is one condition for each trial. And it has the flip numbers. So the flip times are recorded, each flip time is recorded, and the last flip numbers is saved so that you can query, which condition, for which trial each condition number corresponds. So the flip times, the exact flip times on the clock of this computer are recorded here. Now, let's try another stimulus. And this one is a little bit, this one is pretty simple. It's another stimulus, dot, for example, single dot. So a stimulus single dot is pretty simple. It has the background level, the dot level, dot brightness, dot coordinates, X, Y, and dot size, and dot shape, rectangular or oval. And the time, this should be called duration, the dot duration, how long it will stay on the screen. Okay. All right. So it also has its show trial method. It's pretty simple, straightforward, and it knows how to display itself. All right, let's look at its configuration file. I don't have. Oh, yeah, here it is, single dot. So it's also pretty simple, has the same format. So we have the background level, there is no, looks like there is no interval or blank period that we can specify. So you can just specify the dot duration. So a dot is on the screen at any time. And also uses this factorized. This factorized, you don't have to factorize the function. The idea here is you need to create a list of parameters specifying the conditions. And one simple way is to specify some condition with multiple values, and they use the factorize function to multiply the number of to produce all the possible permutations. But this is a common technique, but there are many different ways in which you can create sequences, the right sequences of conditions, including mixing different types of conditions. So then you need to call the make condition. So this does some preparations for the stimulus. For the dot, it's pretty simple, it's pretty straightforward. And then you need to push the trials onto the queue. So this prepares them. So again, let's do stimulus open to open the display. Then stimulus configure single dots. This does the preparation. So the total time will be 100 seconds. And then we do the stimulus run, struct, session. Let's do for the second session. That's what it does. Pretty straightforward. 100 seconds. All right, I'll stop. And then stimulus. So you don't need to do stimulus close. You can run stimulus, another stimulus right away. So for example, we can do stimulus configure gradings. Most of these configuration scripts clear the queue, but you don't have to clear the queue. So you can run several configuration scripts and queue multiple sets of stimuli, right? So have queue them up as you can produce different combinations of visual stimuli. So there, we need to skip it. To be continued. So this again configures now the grading stimulus again. So this the configuration there cleared the. All right, let's look at one a more complex stimulus. It's called Trippy. So this stimulus was used for a big study called Microns, Machine Intelligence for Cortical Networks. It's a stimulus that allows computing receptive fields, orientation tuning, and directional tuning all in one stimulus. So this method has a few things. It's a little bit more complex. It has these numbers of nodes and upscale factor for an efficient representation, temporal frequency, kernel length and time. This is a handing kernel. And so it has a couple of computed parameters that are computed from the rest. And so there is a random number generator seed as one of the parameters, but then you can make the make method. You can create a make callback function for this class. And this will use the random number generator or whatever the other parameters are to add and compute any more additional parameters that need to be computed. But there is also a prepare function. The prepare function computes additional fields that are, you may not want to store them in the database, but you need them for displaying. You want to pre-compute them before displaying, before running. So this is, you typically want to do this instead of doing this in the show trial function, you do this inside the prepare function so that you can pre-compute beforehand. And then the show trial just simply shows the movies. And the rest of this method, the rest of this class has the code to generate the stimulus. So let me demonstrate this, and then I will and then we'll talk a little bit more about how this works. Okay, so stimulus open. And then stimulus configure Trippy. So this has, so it takes a little bit longer to generate the trial, but there are only 4 trials. And let me show you the configuration file. It has 4 random seeds, so there will be 4 different conditions. Each condition will be 16 seconds. And I specify the dimensions, the number of pixels along Y and the number of pixels along X. Then the screen height in degrees. So this is, again, this is used to correctly compute the angular size, the spatial frequencies in the stimulus. And this specifies the representation, how many nodes are used in the underlying representation of the stimulus. And this is the upscale factor. And so these are we figure these out ahead of time. So these are configured. But since only one parameter here is vectorized, that means that there are only 4 different. After we run the factorize function, there are only 4 stimuli, 4 conditions. But we can add them multiple times. If you push them twice onto the queue, then that means the 8 of them will be shown. So if you can see here at the start of the function, we clear the queue, so it doesn't clears any other stimuli that haven't queued. You can remove this, and this will then, you can run multiple configurations. So let's run the stimulus, and while so stimulus run. Okay, so these $ indicate missed frames. I don't typically see this, and so this is usually indicates some sort of a problem with the display, and I think it's because I'm running Zoom, so it's not quite keeping up. But so this is the visual stimuli, and these drop frames are important, and this brings us up to this little corner square that you see. So this framework uses synchronization based on an encoded signal that can be decoded, and if you put a photodiode on and record from the corner of the screen, you will get a waveform that allows you to decode the number and identity of each frame, and then you can use the frame numbers that are so you can record it along with another modality. Say if you record electrophysiology or calcium imaging, you can record that signal and you can decode it, and you can know the exact time within the recording of each frame, even if it's delayed or there's a drop frame. So these drop frames happen sometimes. That shouldn't happen this often, but they happen if the computer, especially if your computer is doing something else. None of our operating systems are real-time operating systems, so we run into these cases where there's some drop frames. So it's important to keep track of individual frame times if you want to get precise displays. So this Trippy visual stimulus was used in the Micron study, and within a short time, relatively short time, within about 15 minutes, you can characterize the properties of cells along many dimensions. And if you have any questions about this presentation framework and recording framework synchronization, please let us know, and enjoy using this element, and good luck.